students. Today we are going to talk about Lensmaker formula. It is very famous formula in regards that how we can design a lens of desired focal length, of desired property. That guiding formula is this Lensmaker formula, and from that we shall also derive lens formula, which you have been talking about since class 10. So here we will take the clue that which we have discussed in the previous lecture, the refraction at a spherical surface when the object is placed in a rarer medium was expressed by equation 1a, and refraction at another spherical surface when the object is placed in the denser medium, and that was expressed by equation 1b. Here we are going to use those two relations, so I will request you to go through the previous lecture on the refraction at spherical surfaces so that you can understand this topic very well. Here we have assumed that an object is placed in rarer medium, say for example air, and we have selected two rays emerging out of the object O. After refraction at the first surface, spherical surface XAP1Y, had there been the same medium continued, the image of this object O would have been formed at point I1 due to refraction at this surface XAP1Y. We have simply draw a freehand diagram and assume that the object is placed over here and image is formed over there, which would have been the real image. Now, since the ray is suffering second refraction at the surface, another surface XBP2Y, therefore the ray is further bending and the image is formed at I instead of I1. And here you have to take care that the image formed by refraction at first surface, which is at I1, serves as an object for refraction at the second surface, and due to refraction at the second surface the final image is formed at I. We have assumed like this. Here C2 is the center of curvature of the surface, spherical surface XBP2Y, center of curvature of the surface XBP2Y, and C1 is the center of curvature of the spherical surface XAP2Y. So the radius of curvature for this of the surface XBP2Y will be C2P2, but we are further assuming that this lens is very thin and therefore P2 and P1 should be very close to point C, and therefore we make some approximation and take C2P2 equal to C2C. Again, in the same way, the radius of curvature of the spherical surface XAP1Y will be P1C1, but we have taken that the lens is thin and therefore P1 will lie very close to C, and so we take P1C1 nearly equal to CC1. This is for our convenience. We have done this. Now the object is placed at point O and its image due to refraction at first surface XAP1Y is formed at I1. this I1 serves as an object for refraction at the second surface xbp2y, and the final image is formed at point I. Now, given this background information, we are borrowing the formula which we have derived in the previous lecture, that whenever object lies in a rarer medium, the refraction formula is given by mu2. It was actually mu2 by v minus mu1 by u equal to mu2 minus mu1 by r1, where v is the image distance, u is the object distance. Here you see mu2 is the refractive index of second medium, which is this medium, denser medium, and that divided by image distance, that is ci1. You see ci1. Again we have approximated this, so ci1 is the image distance. Now co, what is co? Co is the object distance, distance of object from the center of the lens. So for u we have written co, and for v we have written ci1, and radius of curvature is taken to be r1 for the first refractive surface, that is for cc1 we have written like this. For cc1, you see p1 c1 is the radius of curvature of this surface, and that is approximated to be equal to cc1. cc1 is equal to p1 c1, and similarly we have approximated for p2 c2, we have approximated to be equal to cc2. And that is taken R2. Now we name it as equation 1a, and now this image I1 serves as an object for refraction at the second surface, and therefore for this case, that means when the object, here you see this image is as if it is lying in the denser medium, and so we consider the second equation, that object lies in the denser medium and it is suffering refraction. So for that we have the relation, we simply exchange it. You have the relation mu1 upon v minus mu2 upon u. So mu1 upon v minus mu2 upon u equal to mu1 minus mu2 divided by r, equal to mu1 minus mu2 divided by r. Since this is the radius of curvature is r2 in this case, so we write r2, and mu1 upon ci, mu1 now here it should be mu1 upon v, or image distance. So what is the image distance? This is the image distance ci. This is the image of the object I1 due to refraction at the surface xb p1y, and so we write mu1 upon ci and minus mu2 upon u, and that is for u you have ci1. So I believe that you have understood how we have got this expression, and that equal to, we are exchanging mu1 and mu2, so mu1 minus mu2, so mu1 minus mu2 divided by radius of curvature, in this case it is r2, so we write like this. And now if we take minus sign common, in the numerator it becomes mu2 minus mu1, and in the denominator we get minus r2. Now we name it as equation 1b. On adding these two equations, equation 1a and equation 1b, what you see is, here you have mu2 minus mu1 common in these two expressions, so 1 by r1 minus 1 by r2 will remain in the bracket, and that's what we got here. 1 by r1 minus 1 by r2, and mu2 and minus mu1 is taken common. Now here you see mu2 upon ci mu 2 upon Ci is negative here and positive here, so on adding they cancel each other. On adding they cancel each other, and so what we have, they cancel each other, so now we are left with mu 1 by Ci minus mu 1 by Co. So mu 1 by Ci minus mu 1 by Co or OC, and mu 1 is taken common and moved on the right hand side, so we get 1 by Ci minus 1 by OC equal to mu 2 minus mu 1 divided by mu 1, mu 2 minus mu 1 divided by mu 1, and this factor remains there, 1 by R1 minus 1 by R2. And here you see for Ci, what is Ci? You see Ci, this is the final image distance and we name it at V, so we write 1 by V minus 1 by OC. This is the initial object distance, so divided by U, that is object distance, so 1 by V minus 1 by U equal to mu 2 minus mu 1 by mu 1 within bracket, and another bracket start 1 by R1 plus 1 by R2. We name it as equation number 2. This equation number 2 is known as Lensmaker formula. Well, why we call it Lensmaker formula? Because we can design a lens of particular property, particular quality by selecting the value of R1 and R2 to give us the desired results. And this expression therefore is known as Lensmaker formula. It is enabling us to design a lens of desired quality, desired focal length for a given pair of mediums having refractive index mu1 and mu2. So it is not only the radius of curvature which will decide the focal length of the lens, it is also the absolute refractive index of the two mediums, the medium of the lens itself and the medium surrounding it will decide what will be the focal length of the given structure, the given lens. Now if we take u equal to infinity, means, and if any object lies at infinity, the rays are coming parallel from infinity, parallel rays are received from that object if the object lies at infinity, and there all those rays after reflection or refraction meet at some place, and that point is known as focus, and the distance of that point from the principal the optical center or optical center or pole of the device is known as focal length. So if we have u equal to infinity, v, that is the image will be formed at a distance which is known as focal length. So we have, if we have u equal to infinity, v is equal to f. So we have, if u is equal to infinity, then we have v is equal to f, and therefore we have 1 for v we write f. So we have 1 by f minus 0, that is 1 by f, equal to, and on the right hand side everything remains unchanged. So mu 2 minus mu 1 whole divided by mu 1 within bracket and another bracket, in another bracket 1 by R1 minus 1 by R2. This equation gives us the value of focal length of a lens which depends upon the refractive index of the two mediums and radius of curvature of the two surfaces where the refractions take place. So this equation is very useful to find the focal length of a given lens, and also it is expressing how focal length depends on refractive index as well as the radius of curvature of the spherical surfaces of the lens. Now if we put this value equal to 1 by f in the equation 2, that is Lensmaker formula, so on the right hand side we have 1 by f for this expression, mu 2 minus mu 1 whole divided by mu 1 into within bracket 1 by R1 minus 1 by R2. So for the RHS we have 1 by F, and for LHS we have 1 by V minus 1 by U. This is known as Lenz formula. I believe that you have understood how we have derived it, and also students, be careful about understanding the sign convention and applying them, because if you fail to understand it properly, all your efforts in solving the numericals related to ray optics will be futile. So please take care. That's all for today. Thank you and have a nice day.